teachers may have said that this is completely impossible to have a negative number under a square root. This isn't quite the complete truth. In fact, it is possible to have a negative number under a radical. And that is the basis for a new kind of number, actually. Mathematicians define a new number, I. It's just simply a lowercase I is how it's written, and we say it is equal to the square root of -1, quite simply. And this is true. This is mathematical truth, and it is completely valid. Now, what this forms, if you think about it, is really a new set of numbers. We have, I mean, just imagine if we have I equal to -1, we know that I squared equals -1, okay? So I is the number where if we square it, we get -1. And so I have made, and I will continue to make, many more videos about I and imaginary numbers and how they are very elegant in themselves. So I said I squared equals -1, and that's all fine. And now if we add 1 to both sides, just for fun, we can say I squared plus 1 equals 0, right? So if you think about it, what this solves is, the equation x squared plus 1 equals 0. X squared plus 1 equals 0. And in fact, to be more precise, there are actually 2 and only 2 solutions to this polynomial, and they are not just positive I, but also negative I is another solution. So for this polynomial here, I'll say f of x equals this polynomial. The solutions are the set negative I and positive I. And so those are the 2 solutions of the polynomial. Now, I itself is an imaginary number. We can treat it as a number in itself. So we can have some multiple of I. We can say, all right, well, this is 2I or 3I or 7I over 2. We can take some number times I, and we can also, if we want to, we can also add a real number to I, like 1 plus I, or 5 minus I. But I just alluded to something a lot more important. We can say, basically, we're forming this new set, C, the set of complex numbers, which is my favorite set of numbers, actually. And it basically means that every number that is contained in C can be written as A plus BI, where A and B are real numbers, so we're extending our view, or we're expanding our view of what really is a number. But unfortunately, this is really a very good historical idea that an Italian mathematician named Cardano had gotten the sort of idea of imaginary numbers in the 16th century, so it could have been far before the time of the 1800s. But still, it's very interesting stuff. It was really, this is a pretty revolutionary idea that we can take the square root of a negative. And so I encourage you to explore around in complex numbers, and this relates very much, the idea of complex numbers, it relates very much to actually the fundamental theorem of algebra. In fact, the fundamental theorem of algebra, and this is considered relatively advanced, but I'm sure you're able to understand this. I'm very sure, and I'm quite excited to be the one to teach it to you. But in all seriousness, the fundamental theorem of algebra, as proved by Carl Gauss for his dissertation in the 19th century, it basically states that if we have a polynomial, call it, I don't know, g of x, or f of x, some sort of function, some polynomial function of x, of degree n. Okay, so just n is just a variable. That's the degree of the polynomial. Lots of different kinds of functions, but this is a very general fundamental theorem. So polynomial of whole number degree n. And let's say that all coefficients of this polynomial are contained in C, the set of complex numbers. Then, so we know that g of x is a polynomial of degree n, and all of its coefficients and constants are contained in C, so they're all complex numbers, right? Then, and this is a very, very exciting theorem, so brace yourself, this is a very, very exciting theorem, alright? Then we know that the number of solutions in C that exist where g of x equals 0, so the number of solutions in C that exist is exactly n itself. So I'm just going to let you digest that for a moment. It's truly very amazing. This is one of the main reasons that well, we have some thunder. Right, no, in all seriousness, it's one of the main reasons why Carl Gauss is my favorite mathematician. So I'm sure you've seen in the past, for example, with a quadratic equation, ax squared plus bx plus c. And that'll be our function. It's a relatively basic example. We have a quadratic equation simply right here, and we know that for a 2-degree polynomial, and this only works for a quadratic function, basically, polynomial, we have the quadratic formula to help us solve this. So it's the quantity, negative b plus or minus the square root of b squared minus 4ac, all over 2a. And I'm sure you all remember this. But you probably have wondered in the past, what if this discriminant here, this value under the radical, b squared minus 4ac, what if that value is negative? And you've probably been told, well, then there's absolutely no solution. We cannot solve such a polynomial, then. We can't find a solution. There is no solution. But that's not entirely true. With these complex numbers, just imagine, we can solve one of these things. We can find exactly 2 solutions in this case. There are always 2 solutions, as long as a, b, and c are complex numbers, which almost all the time they are. In fact, in the school system, you usually use the set of real numbers, which is even stricter. It's a subset of c, right? So we have b squared minus 4ac. And I'm gonna take a case where that is negative. So let's say we had, let's say we had 7x squared plus x plus 5. Alright, now we can try to factor this, but it probably won't be easy to factor. So what I recommend in this case is to use the quadratic formula. Let's just try it. -1 plus or minus the square root of, then we take b squared, that's just 1, minus quantity 4 times 7 times 5, and we divide it all by 2 times a, which is 14. And so we know that this is really square root of, well, it turns out this is 1 minus 140. That is the product there, assuming my arithmetic isn't flawed. So now we have square root of negative 139, all over 14. And now we know this is possible. This is now possible to have the square root of a negative, right? With complex numbers. So now we can kind of separate this fraction here. We get negative 1 over 14 plus or minus, and then, as I'm sure you can imagine, we can actually make use of the fact that I is equal to the square root of negative 1. Because if we had square root negative 139, I'll just put on the side here, square root negative 139 equals the square root of 139, something that we're used to, something, we can take the square root of a positive real number, times the square root of negative 1. Because if you simplify one side, you get the other side, basically. These two quantities are equal, so we can split up square root of negative 139 to the positive square root, or I should say square root of a positive, times square root negative 1. And we have already identified this as I. So now back to our equation, we know that this is really I times the square root of 139 over 14. Now I'm fairly sure that the square root of 139 is irrational. And I'm not too big a fan of irrational numbers, but I'll save that story for another day. But my point is, we can actually take the square root of a negative in mathematics. Mathematics isn't always about staying within the system that you're used to. It's really about thinking creatively and inventing new kinds of number systems. And C is an example of that. It really revolutionized mathematics, and so I hope you appreciate that. And so where was I? Right, so these are the two solutions. It's plus or minus, so that just designates the two different solutions. And of course, this is just one specific case. This is just one case of polynomial. I was just using this as an example. But just know that this works for all polynomials of degree n, of any whole number degree.